Good evening to everyone, and thanks to the organizers for having invited me. So I would like to speak about our paper that were written in collaboration with Professor Giovanni Vignali from University of Missouri. Sorry, I think it's a little bit, yeah, there is a little bit of mathematics involved, but after beer, I think. So the outline is a brief review about many-body perturbation theories ab initio, in particular GW approximation, beta subsidiary equation, and why there are some problems, some issues in 2D materials because initially these ab initio perturbation theories were developed for 3D problems, bulk problems. Then we speak about our derivations when we use localized basis sets and how the self-energies look like, and some conclusion perspectives. So what is the main goal for this ab initio perturbation theory when we have a density functional theory that works quite well? Well, the answer is that our focus is the steady state properties of matter. In particular, there are two cases. When the system is in a state A, after scattering is a state n plus or minus 1. Typical examples are the direct photon emissions, where a photon comes and an electron is injected, and the inverse photon emissions, when an electron comes and a photon comes out. And the second case is of the optical properties, where the state in the initial defined state is n, but there are two. The electron comes to the conduction band and starts to interact with the hole. So create the quasi-particle that is called exciton. Because here the case schematize the optical spectroscopy. An incident photon comes to the sample and there is some reflected photons and some transmitted photons. So density functional theory is a ground state theory, and if it doesn't work in these cases, it's not his fault. We are looking at something different. Then this is the reason why we need to come out with the many-body, and the typical the starting point is the one particle Gaussian function, where the two states there is you can also call the propagator. So it's creation and destruction of one electron and the recreation to another state. Then there are several representations. One of these is the lemma representation, and where A is the spectral function, and imagine a part of the Green's function. And these objects, actually, the creation here is the destruction of one electron and the mean value of this value, the mean value. And if we see the equation of motion of this object as we see that actually we can rewrite this equation of motion like in a Schrödinger-like equation. So which is called the quasi-particle equation, where now we have an object called self-energy. Well, this self-energy is quite a tricky object because it's in general not local, energy dependent, and even not Hermitian. So it's a tragic operator. But if you see, there are some analogies with the Hartree-Fokker equation, where we have an exchange self-energy, which is only non-local, and the Gaussian, where the exchange correlation potential is local. In general, it's impossible to solve this equation of motion. And one possibility is to use the heading equations. Heading and 65 essentially wrote in a closed form 5 Dyson equations, here in where every object, the Green function, the screen potential screened by the surrounding electrons, the self-energy, and the polarization and the vertices are connected to each other. So in theory, one could solve in a theoretically way this equation and get the evolution of, for instance, of propagator, or for instance, the emission spectroscopy scattering. Unfortunately, you see the vertex is between all of them is a terrible Dyson equation, which involves 4 points object, the kernel, this kernel. So the idea of adding was to say, okay, let's neglect this awful object and treat point like this vertex. So the self energy itself loses this vertex and becomes GW. This is the reason why it's called the GW approximation. Then we have the polarization, which becomes what is called the RPA bubble approximation. And at least in this sense, much more feasible. And the point is this one. If it's, what are the limits of this approximation? Well, why should work? I mean, in this sense, just by experience. So when we started to calculate the band gaps from LDA, this GW approximation, we saw actually that band gaps were in much more better agreement with respect to the with experiments with respect to the LDA DFT calculations. Here there is a picture from a sheet in 2006, and essentially this is the reason why it is becoming always more and more important calculations in nowadays. The second point, what are we neglecting when we remove that awful part in the vertex? Well, we are removing all the ladder, what is called ladder Feynman diagram, that involves the interaction between two particles. So, for instance, electron-electron interactions and electron-hole interactions, which are really important, as said in the optics. The second idea was then to use the Bethe-Salpeter equation, which is a Dyson equation for the two particles Green function. See, this is how is performed nowadays, where the kernel, this awful part that was in the vertex, is rewritten in this way with a random phase approximation. The electron-hole interactions are mediated by the screen interaction in one of the objects in the heading equation. It worked quite well, and there are a lot of papers in 20 years that we showed a lot of examples where the results are very good agreements with the experiments. But when graphene came out, actually these previous calculations were made for bulk. And now we see that why, when QD system, we are affecting problems of QD systems, these are not, I mean, they have some issues. The point is that all the codes, the important codes, are full plane waves in periodic codes that are okay for bulk, but when we are going to 2D materials, we have the Z direction that is empty. And when it's empty, actually, we need to insert many more plane waves. You see here a work in 2015 from Smoot and Stevenson, where they showed actually we need to converge the GW band structures. We need to go up to 500 electron volts. And this is, I mean, it's still quite cumbersome even for our clusters, these computer clusters. So, and it becomes even worse when we are looking at surfaces and plane waves, periodic codes, when we have, for example, vacancies, F defects, charge defects. Well, these charge defects in these unit cells are interacting each other, and you see here another work from Thompson and Pasquarello, where without they had to correct by adding electrostatic potential, and you see how between them correct and incorrect work, how it works. So what to do in this sense, and the point is this one, that the Coulomb potential in GW is even worse, because the Coulomb potential is a long range potential. So the systems can interact with its replicas, and because we are getting involved, the many unoccupied states are getting involved, this can take calculations with thousands of unoccupied states. And this, of course, produces artifacts that slow down the convergence parameter. A possibility was introduced in the 2006 from Carlo Andrea Rossi, where essentially the Coulomb potential is cut off. So instead of using this one in the reciprocal space, they use the typical shape of potential. For instance, for a molecule, you see that actually how has to, I mean, this is the analytical form for when we use this for a spherical cutoff. And this is actually is a very practical approach, and is now implemented in all codes, periodic codes. But we want to use another approach. Essentially, instead of using plane waves, let's start to use, like in quantum chemistry, Gaussian type block types. So here the typical block wave function, then this phi actually can be Gaussian type, one-year function, but then we see we use another function called numerical function FHIA functions. And okay, then the idea was to rewrite all the equations from wave functions with this formalism. The point is here that instead of using the reciprocal space, it's just in two directions, x, y, and it's not periodic in the z direction. So we can, this is our native, they are really in the surface and in the 2D, and we are not exploiting the third direction, so we don't have any interaction replicas with these wave functions. Writing this general formalism, well, I know that here is typical, there is this, the fact that these wave functions actually, these wave functions are not in general orthonormal, so there is an overlap matrix. I know that this quantum chemistry don't like, and they would say it's typical physics, but we will think about like in a metric tensor. In such a way, we have two wave functions which are called covariant and contravariant, like in relativity. And actually, it's the same idea of the relativity. And this makes much more compact all the equations. The orthonormativity is written now in this way, covariant, contravariant, and the completeness of the function. And any wave function can be written in a linear combination. These are the two for covariant and contrariant. And but we look at the Green function, so 2-point function. So this is a general block property for 2D, where the point this is in real space, and when there is transformation in this vector space of the plane wave functions, and in the reciprocal space it's written in this way, where the just matching and sandwiching the real the 1-2-point functions in this way. So the element representation of the Green functions can be written in this formalism, and here always in real space to wave function space, and the wave functions actually here the self energy. Now we can exploit a similar way Feynman diagrams, where, for instance, the vertices are written with these terms. The self-energy is written now in the reciprocal space with a G alpha beta with the wave function space, and these vertices, which are here, that actually are 3 wave function integrals, and this is the most difficult part, to integrate these three body particles. But essentially saying that an electron comes, a photon is injected, and the electron with a different momentum, different is out, and vice versa. Then we need to write the polarization function also, which is important for the screen part. And this is also called the bubble diagrams, because of these are all the bubbles diagrams that are involved in the RPA, so it's a random phase approximation. And so once one writes in this way, the screen interaction, so the Coulomb dressed by all the electrons around can be written by using the polarization and the polarization and the Coulomb interaction. So there is a subtle problem in 2D. Usually when one looks at optical spectrum, one calculates the macroscopic dielectric function as 1 over the inverse of the electric function. And the absorption spectrum actually is in proportional to the imaginary part of this macroscopic dielectric function. However, in 2D materials, when Q is 10 to 0, there is this limit. P, the polarization, goes like Q squared. So, and the Coulomb in QD actually is 1 over Q. So the dielectric, macroscopic dielectric function has not any meaning because it's going to 1. This means that actually we are looking at something that is much more closer to 2D. 2D materials are much closer to the molecules. So we don't have to to look at the macroscopic dielectric function, but actually at the polarizability. The polarizability is going correctly, 1 over Q. So it's much more meaning, has much more meaning with respect to the electron function. So this is typical for molecules, and in quantum chemistry, when one looks at the some spectrum. So here it's again a little bit involved. This is the two body, which is quite a mess. With this kernel ID, electron hole interaction, and there is the exchange part that actually is recovering the polarizability in a random phase approximation, and the change part, the correlation part, which is mediated by the screen part. And see here, always we treat like an evanescent part of the Coulomb part, the Coulomb interaction with an evanescent term, Q8, and typical Fourier transforming when it's in next y direction. This is essentially how usually is performed the integration. One look at, because this is Green's functions, the inverse is can be connected to an excitonic Hamiltonian, and usually it's diagonalized. The eigenvectors, the eigenvalues are actually the peaks, the poles of the excitons, and the intensity of the excitons are related to. The imaginary part is of the polarizability is the absorption spectrum, and you see also there is also an oscillator strength for which is typical in that derivative of the rule. Yes, here the summary of that. Just a key, what are these functions that we localize these sets? Well, we are looking at numeric atomic center basis functions as implemented in FHI and AIM, and these are essentially described by a radial term for inner part in the spherical function, and that there is a cutoff to make it quite localized. And why it's so interesting? They are so interesting because essentially they have a lot of standard and non-standard functional implemented, especially also for many-body perturbation theory, PA, MT, molecular C2, GW, and for molecules. So somehow they already have already settled these problems of long range interactions, and it's a free tool. So to summarize is that we worked on this 3D materials hybrid system between quantum mechanics and solid-state physics. Instead of using plane waves, we use localized basis sets to build block functions. And the perspectives could be quantum, also many body perturbation theories in quantum chemistry problems like defects, physisorptions, kinsorptions, and perhaps quantum chunks problems. So thank you, Professor Yang Ping Feng and Antonio Castroneto, and thank you to everyone